So this is our first unit on limits, and you've had an idea of limits a little bit before. If you go back to grade 11 math, and you go back to your sequences and series unit in grade 11, do you remember doing infinite geometric sequences? Okay, here's an idea. If I would start a certain distance away from the wall, I can walk half the distance to the wall. So if I walk half the distance, let's say I started 16 blocks away, I'm now 8 blocks away. I just walked 8 blocks. If I did that again and walked half the distance, I would walk 4 blocks. And again, I would walk 2 blocks, and I'd be 2 blocks away. If I do the half, I'd walk 1, and half again, half, and then a quarter, and then an eighth, and then a 16th, and a 32nd, and so on and so on and so on. Can you see that I would be getting closer and closer and closer to the wall? But I would never get to the wall. But we would say at infinity, and this is what we did in that geometric sequences unit, if we kept adding those all up, we've got our first term is 8. We're multiplying by a half, so our R value is a half. And going back to that formula you had back in grade 11 for infinity, sum to infinity of a geometric sequence where the R value is less than 1 is term 1 over 1 minus R. And if we put that in, term 1 was 8 and R was a half, we get 16. Now I started 16 blocks away from the wall. And we say I never get to the wall. But if you would do this forever, the idea is eventually you're so close to the wall that we would say you're basically there. And that's the idea of a limit. A limit is something that you can get really, really close to even though you're not getting there exactly. So it's a value you get really, really close to, and we can see this with our geometric sequences that we've done before. Now, as we get into our calculus unit, there's 2 main branches of calculus. There's differential calculus and there's integral calculus. We work with differential calculus first, and then we'll do integral calculus last. Now, integral calculus was used to find areas under curves and areas under shapes that maybe you couldn't do easily. Like we know how to do areas of triangles. We know how to do areas of squares. Speaking of areas of squares, I just learned a new formula for the area of a square. It is, there we go, very important formula. Here's a new formula for area of a square. N is the number of sides that a square has, which is 4. Good. And S is the length of the side. So if we put 4 in for N, what do we get here? 4 divided by 4 is 1. And over here we get cotangent of pi over 4, and you're going to have to go back to those memorized values. What is cotangent of pi over 4? Well, maybe you have to think of tan of pi over 4 first. 1. And so cotangent of pi over 4 will also be 1. So if this is 1 and this is 1, the formula just becomes side squared, which is what you knew for your formula for area of a square to begin with. So you go, oh yeah, this is a really nice formula because it's not very helpful. Well, the nice thing about that formula is it works for triangles as well, and for regular pentagons and hexagons and a regular octagon. And the reason I came across this formula is I needed to find the area of a regular 36gon, 36-sided shape where all the sides were the same. And then I came across that the formula was 9s squared cotangent pi over 36, and I looked up some other formulas and they all seemed to have this format. So then I went and tested myself to see, could I prove that this works for any regular polygon, and it does. So now you have a formula that works for any regular polygon. It works for equilateral triangles all the way up to, you know, if you wanted to find out the area of a loonie, you could do that, because how many sides does a loonie have? It's a regular, it's not a circle. Have you counted the sides on a loonie? Oh, there's your first homework. All right. So, integral calculus goes back a long time. In fact, Archimedes in around, what do I have there, around 300 BC, it doesn't even say, 300 BC, was already developing the idea of integral calculus way before we can say that calculus officially was discovered / invented by Newton and Leibniz in the 1700s. Now, as far as differential calculus, we say that differential calculus was discovered simultaneously by both Newton and Leibniz. They both found it on their own in their own field of study in different times. However, it used to be that if you had a textbook and it was an English textbook, it would say that Newton discovered calculus. And if you had a textbook and it was a German textbook, it would say Leibniz discovered calculus, because Leibniz was German and Newton was British. And they didn't like, they didn't like each other at that time. Academics fought a lot. They weren't very nice at sharing things. You couldn't just upload it and everybody could see it at that time. In fact, you kept your study secret and you didn't want anybody else to find out what you were learning. And so there would have been fighting about who actually discovered it. It would have been a big thing back then. Anyways, in order to get to limits, we need to practice some of our skills. Some of them you might remember quite well. Some of them you probably don't remember as well anymore. So we'll review some of those things, starting off with factoring. Now, for factoring trinomials, there are a number of techniques out there. You might have learned some grouping methods. You might have been able to solve it directly. There's some shortcut methods. What I would like you to be able to do for factoring is recognize that when you're factoring something, in this case a trinomial, you're probably used to the idea that it would be two binomials multiplied by each other. And when you multiply those binomials together, one pattern that you may notice is whatever is the first in those two binomials always multiplies to be the first one in your answer. And whatever is your last two in your binomials always will multiply to be your last number right here. Now, I chose one of the hardest, easiest trinomials to factor. This one right here. This is a hard, easy one. It's an easy one because usually when you start with just an x squared, students say those ones are easier than if you had a 3x squared or a 9x squared to start with. Those ones are more complicated. But if you just have an x squared to begin with, it's easier, right? This one is a hard, easy one because you will be tempted, right? Right now, you will be tempted to write 6 and 4, right? Because 6 and 4 makes 24, and 6 plus 4 makes 10. But the problem is if you try to make negative 24, you have to make one positive and one negative, and then you don't get 12. So this one's a harder one because there's another way to get 24, 12 and 2. And once you figure out that 12 and 2 makes the last one, the outside gets multiplied together. The inside would get multiplied together when you multiply it all through. And you need to get a positive 10x. So it makes sense that your 12 would need to be positive and your 2 would need to be negative. And one thing you should always do when you factor is once you're done, quickly multiply it out in your head and check to see if it's right. Doesn't take that much time. Your math teachers always do it in their heads, but they don't always say that they're doing it. But I always check, did I get that right? When I multiply that out, does it match what I had to start with? Because if you don't do that and you continue a question on and on and on, you might find you made a mistake way later, and then you've got to go back and redo a whole bunch of work. So this is factoring straightforward stuff. This middle one, you know, in English we often use the word FOIL to say you multiplied your first ones, your outside ones, your inside ones, and your last ones. And we use that acronym to help us remember what we're doing. So if you've never seen FOIL before because you've never had math in an English class, that's something that we use often. How many people are coming from French immersion? Okay. So have you ever heard people say FOIL when you're talking to English math people? They use this just as a, you know, how do you say distribute it all or multiply it out? Yeah. So the product sum idea, right? And that's the idea here. The last ones always make that product, and the other two together make that sum. So this was an easy, hard one. This one, we sometimes have a common factor involved. So in that case, we're looking, when we're factoring something, if there's something that all of the terms have, you could factor that out to begin with. So we notice here in all three of these, all three have an h. So we could factor that out. Now once we factored that out, we'd have to say maybe we could factor the inside, maybe not. So if we could factor the inside, it would be two sets of brackets here. One thing that I want you to be able to do is to recognize that if my first one has to be a 3h squared, if it were factorable, if it's possible, the only thing that could be the first ones are 3h and h. Can you see that if it were factorable, that's the only possibility? And if the last ones have to equal 1, the only possibility would be 1 and 1. In fact, in this one, there's not many choices as far as if you were going through all the choices to see what would work and what wouldn't work. There's not very many choices. And if you check what the outside is and what the inside is when you would multiply that out, is there any way that you could get 7? No. So this part can't be done, and this would be finished as far as factoring goes. But you would still need to check that binomial to see if you could factor it or not. So we're looking for something that, in this case, the product would be not -3 and the sum would be 7. And you would say, well, there's nothing that works for that. So this one is already factored when we can take out the common factor. Adding some language. So again, at any time, French immersion, if you're wondering, well, how do you say that in English? Most of the language is straightforward and easy to go by. And for the most part, learning it in English, if you go to university in English and you've taken French immersion all the way through, you're going to be just fine. But there are a few things that are confusing, and you probably know them already, like inverse in English is réciproque in French, and reciprocal in English is inverse in French. So it's like totally flipped. And that's what most of those definitions mean, which is crazy. Anyways, so here we have something, we call it a difference of squares in factoring. And it happens when there's only two terms. There's a difference, that's the subtraction in the middle, and you're trying to factor that. And the only way to get that, and in fact, it's like you have the first and the last one, and you don't, the outside and the inside is gone. And the only way to get the first one, well, there's two different ways to get the first one, but in a difference of squares, when both of these are perfect squares, and they're perfect squares because 3 times 3 is 9, x times x is x squared, 5 times 5 is 25. And in perfect squares, when you have a difference of squares, you'll have one positive and one negative. And then once you factored that, you would check, is there anything more that I can factor? In this case, you can't. This is as far as you could factor. So those first three are your basic beginning factoring stuff. That stuff you learned way back in grade 10. Now we can look at some stuff that's a little bit crazier, maybe some factoring stuff you haven't seen. So now I've got 1 plus 5x to the minus 1 plus 6x to the minus 2. So this doesn't match any kind of factoring stuff that you're used to. In fact, we've got negative exponents here. What we're going to do is we're going to factor out that smallest exponent like a common factor and see what would happen. What would happen in this case, our smallest exponent as a common factor would be the x to the minus 2. What would happen if I took an x to the minus 2 out of this entire thing? What would that look like? What would you have to multiply an x to the minus 2 by to get 1? An x2, an x squared. And what would happen if you multiply an x to the minus 2 by something to get a 5x to the minus 1? You'd have to have a 5x. And if you took the x to the minus 2 out of this, you would just be left with 6. So one way that we can do this is we can imagine if I take that smallest exponent out in front, what would I have to multiply in each of these spaces to get what I had originally? And now that we've done that, what we have left here is an easier one to factor. It's going to be x and x. It's 2 and 3. And again, this is an example of an easy hard one, because to get 5, you can use 2 and 3, but 6 and 1 also gets you 5. But in this case, it is 2 and 3, and they would both have to be positive. And quickly multiply it in your head to check, and sure enough, it works out. So we could write this answer like this. Again, remember our negative exponents, that this means 1 over x squared. So we could write it that way as well. Are you okay that this means the same as this? Okay? One of the things that this course really tries to prepare you for, when we talk to universities say students are coming to university and their algebra skills aren't as strong as we would like them to be. Their ways to manipulate equations aren't as strong as we would like them to be. And what this course does a lot of is practices those algebra skills so that you get really good at them, so that you know that this is equivalent to this. And sometimes we even have different methods of seeing the same type of question in order to figure that out. Okay? So what I'm going to do now is going to show you this exact same question without the factoring out and connecting it to something that you've done before as well. So you can choose to write this down if you want, but we're going to start with this same question. And instead, I'm going to start by writing it as this, as rational expressions. And if you were adding 3 rational expressions, you'd have to go back to your grade 11 math and say, well, how do I add rational expressions together? You need a common denominator, because it's the same idea as adding fractions. Well, I have a denominator here of 1, a denominator of x, and a denominator of x squared. What would the common denominator be? X squared. So this one would need x squared and x. This one would need x and x, and the last one would be fine. Notice what we get. We're going to get x squared plus 5x plus 6 all over x squared. Can you see that that's the same as when we factored out that x to the negative 2 before? So here's a connection between two different ways of looking at the same question. One as rational expressions and just trying to get a common denominator. And sure enough, now you could factor this to be x plus 2, x plus 3, all over x squared. Or you could have done it the other way. So we often have different ways of approaching the question. In this case, I think both methods get you the answer relatively the same speed. But sometimes one method's going to be faster or more efficient than another method. So I hesitate to say you only need to know one method to something, because there's going to be times that something else might be more beneficial, even though more often the other one's more beneficial. So if we limit ourselves to just one idea, sometimes we're holding ourselves back. And this one is a good example of there's two different ways, maybe one is better than the other. So now when we look at this next question, we have to decide, well, which of those two might be more beneficial? Should I factor out the smallest exponent? In this case would be the x to the minus a half. Or should I factor out and change things to radicals and square roots? And what would help me the most? So I'm going to give you guys a head start. I want you to try to factor this one. All right, let's see how you did. For this one, if I look at all of my exponents, the smallest exponent, the negative a half there, I'm going to just see what happens if I take that out. The easy one is going to be the last one. Right? Start off, feel good. Took the x to the minus half out of there. Now, what would I have to multiply x to the minus half by to get 3x to the 3 halves? I'll have 3x squared. Because what happens when we multiply exponents with the same bases, right? What we're looking for here is x to the negative a half times by something equals x to the 3 halves. Well, and technically there's a 3 in front here, but that will just mean that we'll have a 3 in front there. Okay? Now when we multiply, going back to our grade 9 exponent laws, when we multiply things with the same base, what do we do to the exponents? If I multiplied x squared times x to the 5th, I would get x to the 7th. Right? We add the exponents together. So I need to do negative a half plus something equals 3 halves. Well, maybe I will think of that as a fraction as well, over 2, so I have a common denominator. And then it's really negative 1 plus something equals 3. Well, that would have to be 4 halves, which is the same as x squared. So there's some of the thinking that can go on. Of course, at a certain point, you don't write this down anymore. That's just mental math that you do in your head. So now here, I'm going to get minus 6. If I took out a negative a half, I would have had an x to the 1 to begin with. Now at this point, one thing I try to teach my students to do is always take a look. You've got to the next step. Don't rush into something too fast, because you're going to be wanting to factor this as a trinomial, and you might rush into the fact and put 2 sets of brackets here. Take a step back. Always check for every kind of factoring. Do we have a common factor here? We do. So we should take that out, because that will make our factoring lives easier. Okay? This is one thing that we don't do enough of, is we should always try to make our math easier, right? Even in math, I love doing complicated math, but part of the enjoyment of math is trying to do the math as easy as possible. So taking out the 3 here, so if I factor that 3 out, leaves me with x squared minus 2x minus 15. And now my factoring is much easier than it was before. Can I factor x squared minus 2x minus 15? Yes. It's going to be x and x. 5 and 3. The 5 will have to be negative. The 3 would have to be positive. And we're done. We've factored it completely. What are these questions leading us towards? Well, there's going to be lots of times where it won't say factor. The question will say solve, and it will have equal to 0. If that's the case and this is now equal to 0, it's much easier to figure that out. What value will make it equal to 0? When x is 5. What other value? When x is negative 3. So those kind of things, when we factor it, it helps us solve it. And those kind of solving things come up all over the place in any kind of application of mathematics. So this was new. And it's fun to start the first day with something a little bit new that's connected to stuff that you've learned before. Well, this negative 1/2 here, right, that's part of my exponent. So if I have negative 1/2 and I multiply that by x to the 1, then my exponent laws would say, what do I have to do when I'm multiplying with the same base? I'd add the exponents. So if I add the exponents there, negative 1/2 plus 1, I will get, because I can change the 1 to 2 over 2, and then I can add those fractions, I'll get x to the 1/2, which is what matches up over here with what I started with. So the reason I took out the negative 1/2 over here is going back to this idea. When factoring with rational exponents or with negative exponents, we want to take out the smallest exponent as a common factor. So when I look at this question here, I've got rational exponents. My one that's the smallest is negative 1/2. So that's the one that I took out in front. And it doesn't always work, but in this case, once we did that, we got something inside that we could factor further, because it matched up with factoring that we were used to. So that's where I got the negative from, but this negative here isn't a negative out front. And so that's why this stays as negative 6x, because that negative exponent will just affect the exponents of the other ones. Good questions. And the last factoring one that we're going to look at deals with cubic expressions, and it goes to factoring stuff that you did in grade 12. Do you remember the factor theorem, the rational root theorem, synthetic division? Okay, no. Now, the idea of factoring this, first of all, I would look through, does it have a common factor? No. So it's not going to be that easy. Then the idea of this is if you had 3 things all multiplied together to get this expression. One of the things, if you've multiplied a lot of these together, one of the things that you notice is very similar to binomials, that whatever these first 3 are, those first ones will have to multiply to give you this first one. So right now, I know if we could factor this completely into 3 things, which we don't know if we can or not, but if it were possible, it would have to be a 3x, an x, and an x. That's how multiplying works. Okay? If you multiplied all of these out, to get minus 10, these last 3 in each of those will have to multiply to give you that last one. The problem is it's not as easy as binomials where there's just an outside and an inside. I guess there's a bunch of outsides and a bunch of insides. So this is like, I don't know how it all works. And if we use the New England foil, I'm not sure that rolls off the tongue as nice as foil. And it doesn't really work that well. But this is basically what's happening, is all those things are getting multiplied together. And this is what you would get. Now, the factor theorem and the remainder theorem says if something is a solution, right? Let's make up something right now, even though I know it's not going to be right. But if I want to get minus 10, can you see that I could have plus 1, minus 2, and plus 5? That could be a possibility. If this was a solution, that would tell me that x equals 2 and x equals minus 5 would make it equal to 0. What the factor theorem and the remainder theorem look at is they say if you plug in a number, if it's equal to 0, that tells you you know that it's a factor. So if we plug in 2, and we do 3 times 2 cubed plus 4 times 2 squared minus 9 times 2 minus 10, if it's equal to 0, we would know that x minus 2 is one of our factors. So taking a step back, what we're going to look at is we're going to look at this last number. And we're going to say, well, there's going to be some nice factors. To get 10, it could be 1 and 10 or 2 and 5. That's the way that you could get 10. And because we're dealing with 3 possible factors, it could be positive or negative 1, positive or negative 10, positive or negative 2, positive or negative 5. These are possible roots. There would be additional possible roots because of the 3 in front. You could have 1/3, 2/3, 5/3, 10/3. But for what we're going to do is we're going to check the nice numbers first. Because even though positive or negative 1/3 is a possibility, if you're doing mental math in here, would you rather plug in 1/3 or 1 to start with? You'd rather plug in 1. So we're going to try 1, and we're going to try negative 1, and see if any of them make it equal to 0. Because then that will tell us what one of the factors is. If they don't work, we'll try 2 and negative 2. Which one should we try? We should try negative 1. So if we plug in negative 1 for all the x's, we'd have 3 negative 1 cubed plus 4 times negative 1 squared minus 9 times negative 1 minus 10. And this will be negative 3 plus 4 plus 9 minus 10. Yes! It's equal to 0. How nice. What that means is if negative 1 makes it equal to 0, that means that x plus 1 is a factor. And our original function f of x will be x plus 1 times something else. Now, our synthetic division review, if you know something is a factor, and we would want to divide by x plus 1 to find out what's left, synthetic division looked like this. You take your original function there, which was 3x squared plus 3x cubed plus 4x squared minus 9x minus 10, and you would write those values, just the coefficients, 3, 4, negative 9, and negative 10. If one of those values was missing, like if there were no x squareds, you have to remember to write a 0 in where that x squared was. If we're dividing by x plus 1, we always put the opposite sign outside. You bring the first number down, 3. Multiply negative 1 times 3. Get negative 3 there. So this gets multiplied by this and goes there. And then you add. 4 plus negative 3 is 1. Then you take your negative 1 and multiply it by your 1. And you would get negative 1. And you add again, giving you negative 10. One more time, you take your negative 1 now times your negative 10. You will get 10 and add and get 0. And that's what we were expecting to find because this one was always our remainder. So what it tells us are synthetic division. We found out that x plus 1 is a factor. I'm going to rewrite our function. Instead of writing the whole thing, I'm just going to write f of x. F of x was our 3x squared, 3x cubed plus 4x squared minus 9x minus 10. It's now equal to, we knew that x plus 1 was a factor, and when we took x plus 1 out, we were left with this, which is 3x squared plus 1x minus 10. And now we can say to ourselves, can we factor this further? Well, if we could factor this, it would be two sets of brackets like this. Again, the idea that I'd like you to go from is to get 3x squared, there's only one option to get that. The only way you can get 3x squared with your first ones is a 3x and an x. Now to get 10, there's lots of options. There's 5 and 2, well, not lots of options. 5 and 2, or 2 and 5, 1 and 10, or 10 and 1. And it's important that I list them differently because 5 and 2 and 2 and 5 both make 10, and it doesn't matter the order. But when I put them here, it does matter the order. For example, if I put the 5 here and the 2 there, when I multiply this out, can you see that the outside is going to be 15 and the inside 2? Does 15 and 2 ever make 1? No. But if I put the 2 here and the 5 here, my outside now is 6. My inside is 5. Do 6 and 5 ever make 1? Yes, if we're subtracting. So if I wanted a positive 1x, I would need my 6 to be positive and my 5 to be negative. Because now my outside would be 6x, my inside would be negative 5x, and that makes 1. Again, I do a quick check. If I multiply this out, do I get 3x squared? Yes. Do I get a minus 10 with my last ones? Yes. And do the outside and the inside make plus 1x? Yes. And so now we've factored this completely. We use the factor theorem. We notice that sure enough, all of our last terms multiply to make negative 10. And we've picked negative 1 first to find this factor. The question would have worked the same if you had plugged in minus 2 and found out x plus 2 was your first factor. And probably you wouldn't have thought to plug in positive 5/3 because it's not very much fun mental math to do, but it also would give you equal to 0. But the synthetic division with rational numbers isn't as nice. It's doable, but for the most part in grade 12 we only used nice integer values. So we're going to, when we factor these, look for those integer values first.